Here we're going to start to look at distillation columns. We'll just take the previous simulation, which you may have noticed I switched back to the heat exchanger I had previous. We're going to take that and just expand it a little bit and to include some distillation. We'll first look at TPXYs to kind of look at the feasibility if this is even possible. Then we'll get into using that different unit operation, specifying it, running it, looking at the results. Again, trying to solve some problems with it. Run it multiple times, different things, and then maybe at the end of the time, if we've got some time to look at just other distillation scenarios, already done simulations, we will take a couple minutes and do that. So we have this simulation which we finished with. There was a question on the heat exchanger in the previous, and I switched that out. I swapped it back to the one that we've had. So the question is, we want to separate further than just this flash, the ethanol and water, which my guess is most people are familiar with enough to know that they can be separated via distillation, and they are going to form an azeotrope. If this is not necessarily so apparent, which other components it might not be, you may want to take a look at some different thermodynamic properties and options to see if distillation will work for you. It's probably a very first good step to know to doing before you even get into distillation itself. So we can do some analysis on these components. If we look at a TPXY, our first component is going to be ethanol. Our second component is going to be water. Constant pressure, sure, that will be fine. We can change it to constant temperature if we want, but we'll use 50 if you remember from the previous example. Stream 1 and Stream 2 were at 50 pounds. We will just leave it at that. Number of points, by default, it's 10. We want to see a few more than 10, so we'll put in 100. We don't have a third component in this case, but you could use that if you want. This is in mole fraction. I'm going to change it to weight fraction. And we simply click OK. Now, if you see along the bottom here, we've got some multiple tabs. We didn't talk about that in the previous, because we didn't have anything additional really. When we do a TPXY plot, we get all the data first in the internal report viewer of what was plotted. And you can take a look at the raw numbers if you would like. For our purposes, we're just going to close this. We can close it by clicking this little X here, or the lower X up here. And we get into our plots of the TPXY. We got two different plots. We'll go over this one first, which it considers A2, and then we'll look at chart A1. This plot is read by ethanol in water. And it's ethanol in water because on the previous screen, when we selected it, I picked my first component to be ethanol and the second component to be water. If I had switched it around, it would read water in ethanol. So this is ethanol vapor fraction. This is the ethanol liquid. Whatever is not ethanol in the liquid is water, since it's just a binary system. Since this is above the 45-degree line, we know that this is the lighter component of these two components. We can tell that just by how it's plotted. If we did not know anything else, just we plotted two components, we could tell that by how we selected it that this was the lighter. Where it crosses this 45-degree line is the azeotrope. We can zoom in on that just by clicking, holding, and highlighting an area, and we zoom in on the chart. Here or so, where we cross this line, is the azeotrope. We can zoom in a little more. I didn't quite get the right spot. It looks like it's over here. So I can zoom out. I zoom out by right-clicking. Zoom in again. So it looks like the azeotrope in theory is about 0.95996 or so. Although right here it's really close and it's probably really hard to get to. There is some space here at 0.955. So this should be feasible to get to, in theory. We want to zoom out. We just keep right-clicking. We can zoom back out in the order that we zoomed in. If this was switched and the water was in ethanol, we would have this plot and the line being down below, and I will replot it in a second and show you, and we would get it somewhere about 5% would be crossing the line, just the opposite of this one. Our second plot is looking at ethanol as a weight fraction. Again, ethanol in the water, since ethanol is the first component, it represents the ethanol. Just subtract to get the weight fraction of the liquid, of the water. Anything above in this section is all liquid. Anything below down here, I'm sorry, anything above up here is all vapor. I had that backwards. As you can see by the dots, this is the vapor line. Anything below down here is the liquid range, as you can see by the liquid dots. Anything in between these two curves is a mixed phase. So what we know from this is that the upper temperature is going to be, the hotter temperature is going to be 280, 281.1. If you hold the cursor over, you get a little thing pop up. And the lower temperature, the colder temperature, is going to be somewhere where this azeotrope is, right around 235.5 or so, a little less. Call it 236 just to be safe. Again, we can zoom back out. Okay. So I'm going to put that on my screen up here just for reference. This might be a good spot to put something in the notes, but because I want to be able to, for a quick reference, I'm just going to put it up here. High temp to 81, low temp to 80. Oops, I had that backwards. Wait, yeah, that's right. No, 236. Okay, confusing myself. Okay, so to look at the plot one more time, if we wanted to switch it around, we could. Ethanol and water, and we'll see what I'm talking about. Here's the data again. We close it. Everything is down. Now we know that we picked the first component that we picked, I should say, is the heavier boiler. It's going to go out the bottoms. Same thing with this line. But the temperatures are still the same, 236, 281. We didn't change any of that. Thermodynamics is very important to how we do these calculations. So if we want to look at some different thermodynamic option, we can. We simply, let's pick Wilson. That's another activity coefficient method that will show, as you can see, we got binaries for these as well. It changes back to ethanol and water. Okay. Close this. We have the curve's pretty close to the last one. It still shows azeotrope and such. It has a little bit different shape, but not a whole lot. We can zoom in up here. And we can see Wilson says that we can get to more like 0.97 for the azeotrope. Maybe, you know, somewhere up in here. So it says we can get a little bit closer, or we can get a little more pure. Which one exactly is right? I'm not 100% sure. I don't do ethanol water distillations for a living, but if that's either your job or you're doing work for someone, those are some of the things that you got to check and see which one. If you're interested in getting up to that spot, if you're not interested, it may not matter at all. One more check here. We'll pick one other. We'll pick ideal vapor pressure. If we just did it under non-ideal circumstances, we didn't worry about the azeotrope and things like that, we can show this as being a perfect split. CHEMCAD can do this calculation, and it will split everything perfectly, and people would say CHEMCAD is wrong, and I would argue with them that CHEMCAD is not wrong. In this instance, CHEMCAD did the calculations that you asked it to do, and it just wasn't reality. And here's where thermodynamics plays an important role, because if you did do something like this and it's not reality, that is up to the engineer and the user to understand that that has to match really what is happening out there. So we know this is wrong. I just kind of want to show it real quick as an example of just how picking a different thermal can lead to very different results. Now it's very important to get the thermal correct. We'll use NRTL, and we'll go with that for right now. In a second, we maybe look at something else, but we'll go with that. So now we need to get distillation in here instead of this flash. Distillation columns, we have 4 of in CHEMCAD. The first one I'm going to talk about is the shortcut column. It's kind of the old, just kind of McCabe Thiel, kind of stepping it off, using simplistic approach. It's not very rigorous. It's typically used, the only spot we really see it used in is academia to kind of get people understanding of distillation, setting it up. It's good for kind of predicting where a feed location may be, but for typical industrial users, we'll not use that because it's not as rigorous. They'll use one of either SCDS or Tower, or possibly Tower Plus if they're doing crude distillations. I'll talk about the distillation, the differences in a second here. SCDS is one of the type. It stands for Simultaneous Correction Distillation System, if I've got that acronym correctly. It basically uses what's called the simultaneous correction algorithm to solve it. When you have a distillation column, you've got material coming in, and then you've got material going up, vapor that is, material going up each tray, and you've got liquid going down each tray. So you've got a lot of set of equations where you've got to balance the mass and energy on each tray for the flow going up and down, and that's how that's done is different numerical methods. Simultaneous correction is one of them. The Tower uses the inside-out algorithm. Again, just a different mathematical scheme to get to the same answer, more or less. For these 2 distillation columns, the way majority of the time there are some really weird instances where you have multiple solutions, but there's only going to be one solution. They will both find that solution. They'll just take a different path to get there. SCDS can do a couple of different things that Tower cannot do, or additional things I should say. It can also do reactive distillation. It can also do mass transfer distillation, where we use packing and mass transfer on trays. And it can also do true species electrolyte simulations, which Tower cannot do. So if you have any of those instances, you're going to use an SCDS. We'll see a couple of examples of that if we've got a little time in a little bit. For right now, though, that's kind of a more advanced topic, and we're not going to cover necessarily right here. The difference then between Tower and Tower Plus is if you're going to be doing crudes, pump arounds, things like that, Tower Plus can handle those types of additional features. The majority of time, it's kind of thought that SCDS is used more for in the chemicals, and Tower is used more for hydrocarbons and crude distillations and stuff like that, but either can be used in either circumstance. We're going to use an SCDS column. We can just simply swap this unit. If we right-click the unit, we get the menu options for that unit, and we click Swap Unit Op. Click OK there, and we click the SCDS. Again, we've got multiples that we can pick. Very similar to the question on the heat exchangers. Whichever one you pick, that when you double-click and see the dialog screens, they're all going to be the exact same. This is just a pictorial representation of what your column actually is, either out in the plant or that you're going to be building, that sort of thing. So this one looks like it's got lots of feeds and outlets, and looks like it's got some trays. This one looks like it's got 2 packing sections with a reboiler and a condenser. This one looks like it's just kind of real plain. This one's got 2 packing sections, no reboiler, no condenser. They're all the exact same. You can pick whatever one looks closest to what you think it should look like, but ultimately it doesn't really matter what it looks like. We're just going to pick this one. You can drag it up here and kind of rearrange some things. It does not matter where this is fed. We'll see in a second what I'm talking about there. But just for better visual, I'm going to reroute it. Reroute stream. I'm going to put this in the middle. Somewhere closer to the middle at least. Now, we can double click this, open it up, and start looking at it. Here is where you specify what actually is happening inside this distillation column. So regardless of the picture, regardless of where this stream is routed to, the information that you specify on these dialog screens is what is going to control everything about this, the distillation column and the simulation. So that's why I say it's just a pictorial representation. What you specify here, where it's located, as well as the information here for the condenser and the reboiler, will govern everything. Again, paying attention to the green, we see that we've got to put in the number of stages. Let's just say, let's see. Bear with me 1 second. I forgot how many stages I put. Okay, we'll just put it at 30 stages, and we're going to feed it in the middle. So again, regardless of where it's drawn, I said it's feeding on stage 15. That's where it's going to be fed. We don't have to specify anything else on this screen. Anything additional that you want to specify, you can. It just kind of makes it a little more exact, a little more in-depth, a little more detailed, but it's not needed. This is enough to solve the equations. Under specifications, again, we've got the green. No condenser and no reboiler is a legitimate specification. Take the instance where you have an absorption column where you feed liquid at the top and vapor at the bottom. The liquid falls, the vapor rises, they contact, and that's it. There's no reboiler, no condenser. If we left it here, in this case, it would basically just act like the flash unit did. So we want to put a condenser and a reboiler in. The simplest thing to do is to specify reflux ratio or maybe a duty or possibly a temperature. We know what the bottom temperature and the top temperatures are going to be. The cooler or the high temp is going to be the reboiler or the bottom product. So we can put that at 281. The distillate temperature is going to be the cooler one. That's the top. A 236. Every distillation column in CHEMCAD follows the same format. We start numbering at the very top and we number down. If there is a condenser, that is stage number 1. If there is a reboiler, that is stage N. In our case, stage 30. So you actually have 28 trays, stages inside the column with one reboiler, or one condenser at the very top, being number 1, and number 30 being the reboiler at the bottom. The convergence page kind of just goes over some of the information on just getting it to converge. They're not always easy to converge, and it also, anything grayed out here is the calculated results we can see. And we can also do some cost estimation. We're not going to cover that in the CHEMCAD Essentials course, but just know that that's also possible and additional screens that you could look at. We click OK, and we right-click, run this unit op, run started, run finished. See, we get some information back on the run trace. We can look here. We got no errors, so some of that information is starting to come back to us. Did exactly what we asked it to, 236, 50 degrees, and that's the split we get at that temperature specification. How pure is that? Good question. We can check that. CHEMCAD can tell us that. If we click on the component unit, we get a little drop inside where the units are, that is. We get a little drop-down arrow, and hit the drop-down. We can change this to different things. One I was talking about earlier, that we set up the different units. We can set these here at this stream differently than other places if we want. This will only change these units viewed on this particular stream. It won't change it on any other streams. We got roughly 87% pure ethanol off the top. Well, we know from the TPXY that we can get more pure than that. With NRTL, we can take that up to roughly about 0.955 or so mass fraction. Well, let's change it to a weight fraction, and let's do some calculations that way. So we don't have to do a temperature. We can change it to a mass fraction. Let's first look at this. Well, first let's do this. Getting a little ahead of myself. Okay, so we've got to run. We've got calculations done. We know it's about 87% pure ethanol. And to do it, this is the duties that we needed: reboiler duty and condenser duty. I'm going to put those on the stream here with temp. Condenser was 0.441. Okay, so with just the temperature spec, that's what we did. Well, let's change this a little bit to, we still leave that. Change that back to temperature. Okay. All right. The talk, so we left it at the temperature spec. I'm starting to confuse myself here. And we're going to change this now to Wilson. We saw when we looked at the TPXY that they got slightly different answers up at near the azeotrope. But it also did predict the azeotrope, unlike ideal vapor pressure. So maybe Wilson is legitimate to use and not NRTL. We know ideal vapor pressure is not, because we do know there's an azeotrope. And we can run this again. We should still get, we got slightly different weight fraction. Now we're at about 0.92 instead. Our heat duty went up slightly. Still pretty close. If we change this, now we're going to change this to being component mass fraction, and let's do it at the 0.92 ethanol. Component mass fraction 0.001 ethanol. We can specify it this way as well. We don't, like I said, we don't have to do it via temperature. If we specify it like this, that means, and you can see once we pick some different mode, more things popped up in green, more things that needed to be specified. In this case, we want 92% purity ethanol, and we want no at the top, and we want no ethanol at the bottom. You could have specified this as 0.999 water if you want. Mathematically, there is a difference between doing it that way. For a two-component system, it's not that big of a thing, but if there was more than two components in, this is different. That means no ethanol at the bottom, leave whatever else it is. The other way would be make sure it's mostly water and other things that might have to go at the top. So there is a little bit different. For two components, it doesn't make a whole much difference. And let's run this. Come back in here to convergence, so we're at 0.559, 0.92, so we hit that. Okay, and then let's change this back to NRTL, and let's see what it does at 0.92. Yep, we're at 0.92 with NRTL, and like I said, down here we can see which mode we're in. Coming here to convergence, 0.66. So that's still pretty close. It's a little bit different, but they're within the same ballpark of each other. So it's still not necessarily quite clear on which one's exactly right, but either one of them are probably pretty close to each other at this range and this purity of the ethanol. So at 0.92, we'll start tracking this a little bit. Again, probably a good spot for the notes, but just visually, so I can kind of keep track of this as we're going through this particular problem, I'm just going to leave it up here. All right, we want a little more pure than that. We know we can get more pure than that, so let's move it even closer to the azeotrope. We don't really have to move this any because we already basically have no ethanol out the bottom. We're driving it all out the top. Let's see, 0.94. We can double-click, go into the dialog screen, and see the duties. We can also see them right here, too. Well, 1.67 and 1.4 are our duties now. So we've gone up a little bit, which we would expect if we're getting a more pure component. Well, let's take it even more. We are pretty sure we can get 0.95 by that TPXY that we were showing earlier. Run started, run finished. If you notice that sometimes I use just run this unit up and sometimes I use run all. In this case, there's just no really rhyme or reason why I pick one or the other. This never changes, so this run all or run this unit up is basically doing the exact same thing because I'm just using this one unit operation, but everybody does things a little different. So we made it to 0.95. And we've seen our condenser duties jumped quite a bit. So let's record that one. Okay, now if we're really brave, we'll take it even closer to the azeotrope. We saw on the plot that there was some space between at 955, so possibly we can get it. We should be able to get it calculation-wise, in theory. In this case, if you see the simulation down at the bottom, where I move my cursor to, it is taking much longer to do these calculations. The math is just much tougher when we get in a narrow range like this. Everything that I've done up to this point has been really simple, really quick, and it kind of gives the illusion that CHEMCAD can do distillation super easy and really quick. For the most part, it can do it very easily and very quickly if the math says so. But no matter what, all problems are different, and sometimes the math is just much harder to do than at other times. What this is telling us, and we can see we got yellow, that is a warning. It says what I specified, CHEMCAD couldn't come to a solution, so it tried to find its own solution, something different. Let's see what it came up with. Not really too close. Okay, so let's move this back to 0.95, which we knew we could do. And this is where doing distillation starts to be a little bit more of an art than a science. We can get to 0.955. That graph shows us that we can. We just have to change the math a little bit on how we get there, because the math we had been using isn't going to do it. When CHEMCAD runs for distillation, it's got an initialization that it has to start with. We kind of talked about the difference between the simultaneous correction and the tower, and they've got different algorithms for all of the trays going, material going up, the vapor, and the liquid going down on each tray and all that. In order to solve all those, it has to start with a guess, some sort of initialization, some starting point in which to start doing the number crunching. If that initialization or that initial guess is a good initial guess, it will get there really fast. If it's a bad initial guess, it will get there, it will go the exact opposite way really fast. So what this is telling us is what we used to get to this point for 0.95 was perfectly fine, but it's not a very good estimation or starting point if we want to get to 0.955. So what we can do is say, well, that's fine. Let's find a different point to start from. We know that 0.95, which we got right here, solved the got converged, and so we have a solved solution at this point. We can change this initialization to reload column profile, and now instead of taking the guess that CHEMCAD had been coming up with and starting from that point each time, it's going to pick the last column profile that was solved, which in this case is the 0.95 solution. And then we can move up from there, 0.92. Oops. And that's solved. 0.93. That's solved. We may have been able to jump right to 0.955, but that may have been too big of a jump from the initial starting point to where we wanted to go. In this case, we're kind of moving incrementally because the previous solution in this case is going to be very close to the next solution, which makes the math easier. That's what we're kind of shooting for. And if we do it one more time, 0.95, run this unit up. Now we've solved it, and it actually ran really quick to get to that. If you remember when we used didn't change the initialization and we just used the default, which is auto estimation, it took a long time to run and it still never found the solution. By using the reload column profile and changing it just a little bit from the last variation that we did, it ran really quick and it got to the solution. Let's double check to make sure. 0.95, so we're a little over, but that's 9.5. Sorry, 9.55 what we were going for. That rounding wise is 9.55. Right, I'll just, oops. And we can come in here and we can check the duties now. And we can see the duties start to go off the chart. Start to get really high. So it doesn't really make much sense to do it, to run it when we get this close to things. But mathematically it can be done. And there may be certain circumstances, maybe not with ethanol water, maybe with something else, that you have to drive the simulation, the distillation in reality really close to a point like that, that you might get hard math to solve and a really big increase in the duties. And you can just see, just stepping up, 2% wasn't that big of a deal. 1% here was quite a bit, 10 times the amount of steam. And then 0.5% from here was even greater. And you could have predicted that by looking at the TPXY. So again, some of the tools that you can look at for distillation without even actually doing any distillation. One final thing here we can check, we can change this back to Wilson again to see what we got. Yes. If you remember, the reboiler duties were like 1,300. And if we run it with Wilson, run finished, that's good. It converged, that's good. When we look at the duties, the duty is 1.5. In this case, that is an incredible difference between the duties in the simulation. When we looked at it at 0.92, they were off a little bit, but 1/10 of an MMBTU. Now they're off thousands. So again, this is where if you have to drive some distillation that you've got really to a tight point on the TPXY or really close together, close boilers, however you want to look at it, where you need a lot of duty, your thermodynamics is going to make a difference. If you're out in an area where they separate pretty easy and stuff like that, then there's not going to be much difference. It's not nearly as important. So it's one of those things where it's a calculator. It can tell you a lot of different things, but you've got to know what is the right answers and understand, is this reality or not. Now that we have a converged simulation, this distillation column, we've solved the problem, we've taken it up near the azeotrope, we've gotten it 95% pure. We can start looking at this column and seeing some different information about it. We can do report, unit ops, select unit ops, and that was already selected because it had it, so we can see some information here. We can, I think, under plot, unit ops, heat curves, different things, column profiles. You can also get there by doing plot column profiles here. So if we want to say look at the temperature profile across we can. And we can see, we can start plotting some of this information, some of the different things. Because we've got kind of a discontinuity here, it's not smooth, it comes, stops, and then drops. More than likely, that is not a very good feed location. That's kind of what this plot tells us. So we may want to go and investigate what's the best, or what is a better feed location for this. Now there's different tools. We'll get into that a little bit later with some sort of sensitivity study and things like that. But there are different ways to do some analysis on this. Just by changing this feed location, that may drop our energy requirements some. We can look at vapor flow if we want, how much is going through, a lot of different things. We can even look at actual components, how much in liquid phase, flow rates, plot components, ethanol, water, how much is going up and where it's going up and things like that, to start diagnosing our column, start getting some more, start getting more information about the column now that we have a solved solution. So we can use it to solve the problem of, what are my duties. I can, as it's set up, we can use it to do some analysis and some diagnosis of the column and different things like that when it's operating, or how it's currently operating if we put in the exact, or design basis, where's the best spot, how big do we want it. You can come in here and change the number of stages. Let's just put in 40. In this case, we run it. Making the column bigger should give us less energy. It did a little bit, didn't make a much difference because it's not a lot of energy at this point. It's not a hard simulation to do, but it did drop a little bit. So all these different things are possible now that we've got it set up and we've got the model running with distillation. Okay, I'm going to save this at this point. I've got a couple of other just generic examples that I'm going to show you, just some variations of distillation, and then we will get into the questions. So first, save as. We'll just call this topic 2. Okay. I'm going to close this. Earlier I mentioned the My Simulations folder is where we start as the default for saving files. Under that folder, we have an examples folder. And the 6.53 simply refers to the version of CHEMCAD that those examples were installed with. So you may get more examples 6.52, example 6.5, different things like that. That's just because each version of CHEMCAD puts its own folder, examples folder directory. More or less they're the same. Sometimes we do make changes to them and stuff like that. Sometimes you use them, so we don't want to change them on you. That's why we put a new one each time. But these examples are for you to use, look at, be inspired by, just take and tweak yourself to use, that sort of thing. But none of it's proprietary. If it helps, fantastic. That's the whole point of them. Let's look at distillation and absorption. Let's look at this one, this wet sulfurization, desulphurization of flue gas. Open it up. We can use some of these zoom tools. This one is zoom to fit. If we click this button, it'll make it fit in the exact, within the workspace that you've got so you can see everything. We've got an absorption here. We don't have a condenser and we don't have a reboiler. So we've just got lime and water coming out the top, flue gas, we're scrubbing it, so we got cleaner gas out the bottom. When we can right click, we can edit unit op streams. We see all streams coming in and going out of a unit operation when we do that. So we can kind of see what we've got. Calcium carbonate and water, sulfur dioxide, carbon dioxide, and when we go out, the clean gas, we've got rid of almost all the sulfur dioxide, so on and so forth. Scrubbing. We are using electrolyte, the Pitzer model. Stages. So we see now we have 2 stages, or two different feed locations, so we need to specify both of them. In this case, we got no condenser, no reboiler, so one is the top stage, 2 the bottom. We're doing a regular VLE. But we have electrolytes enabled with this one. So we can actually look at things like the pH of the, where is it? There. pH of 0. Let's look at this. That's a vapor. It's not going to make it. The pH of 6. So with electrolytes, we can start looking at some of those, but we have to use the SCDS to do it. That's how you'd set up something with an absorption. This one looks very similar to the previous. Again, just an absorption. We got water and HCl, and we've got acid, nitrogen, and oxygen as the vapor. The difference being with this one is, again, we're looking at aqueous, so it's kind of an electrolyte type model. But we don't have feed stages now, we have segments. And the reason is that because we have done a packed column mass transfer. Simulation model before was regular VLE, now we've got packed and tray columns. The only difference here, if we click OK, before that was it. The screen closed and we were done. Now when we click OK, CHEMCAD realizes that, hey, since we're in packed column, we need more information. So we get into the packed column screen. If we picked mass transfer with trays, we would get into the tray screen. Again, the green is the minimum. We put in the diameters. We got just one section. We got a couple different calculation methods. Since we did Bravo, Roche, and Fair, we need to put in the information for the Bravo, Roche, and Fair method. If we selected a different method, different would turn green for that. But we have a lot of packing in here, native. That you can pick from. And you can see when you pick it, this one says, we don't have anything for the Bravo, Roche, and Fair method, but we do have the Billet and Schultes coefficients for that method. So you'd have to change this to, in this case, to the Billet and Schultes. That's how it would work. But you can set up mass transfer with packing and stuff like that if you've got something along those lines. One final one to look at, and then we'll get to questions. You can also set up something obviously more complex. What we looked at was less. It was just a single unit operation. In this case, we have a reboiler built into the column, but the condenser is not here like it is in this column. Just pictorial, we could have said it was there, but we chose to pick no condenser. This is the condenser, and then this is the draw for the condensed material. This is just excess going out, vapors going out the top. We've got nothing. We've got two liquid phases in this condenser, and that is what is driving the difference between these. The light phase in this flash comes off the top and gets recycled back into the column, just like a reboiler would do. We just have put all of the equipment outside of the and are separating, simulated or calculated it separately. The heavy phase is dropping down the water and going into this distillation column, which we are calculating just as we've done in the past, with condenser modes and reboiler modes specified, meaning we have a condenser and reboiler built into the column. So this is another way that you can set up a column. You don't have to put the condenser and the reboiler inside compacted with the calculations. You can choose to do it outside of it if it's a slightly different setup than a standard and normal, that sort of thing. So it's just another option that we've got. And obviously these are not the only variations. There are tons more. These are just a few to kind of give you a feel for things. To recap, that kind of concludes the discussion part of it. the presentation part at least, we played with the swap command, which we had seen before, as well as the reroute command. We took a look at the TPXY just to see if thermodynamically is feasible, as well as if we explored different thermal options, what changed, and kind of discussed which one would be the best, and kind of checking stuff like that. We set up a column, we ran it, we read results, we changed some things, we had a problem that we were trying to solve. We were trying to get to a 0.95 or greater. So we tracked how we got there, what happened as we moved up. We looked at other and we looked at other examples of how we go about doing things. So that kind of concludes this. We've got a couple of questions. So the first question is there any way to renumber streams or unit ops to be in order of the flow if they're not in order? Yes, that's just a general question that actually I should have covered in the first segment, but I did not. So if you, like for example this one, this is stream 2, I mean 3, and then 4 is down there, 5, 6, 7, 8, 9. But you want this one to be 10 and then 11 going around. You can simply right-click, change stream ID, and you can make this 10. And click OK. Now, like I said before, no two can have the same ID. But so what happens is 10 is already being used someplace else. If we click OK, CHEMCAD knows this. It says stream 10 is already used. If you click OK, it will just flip-flop those two numbers. Cancel just stops everything. So if we click OK, it's really little, but oops, I'm not sure why. Format, font. How big it is. You can see that those two got switched. So you can go through and go one by one and change all of the ones that you want, that sort of thing. The same thing can be done with unit ops. You want that one to be 7 instead of 6. Click OK. It says it's already in use. Click OK, and it swaps them. So that's how you would change them. You can reorder them into the way that you want them to be. So that was the first question. The second question that we had was touch on how you would determine what number of stages to start with or when to change that parameter. In my opinion, it's usually a guess. There are different calculations that you can use by looking at the TPXY and counting off stages that way. Changing the parameters, you would want to increase stages or stage location to lower the energy in the column. Now, if you lower the energy in the column, you have to make the column bigger, which means there's a capital cost to that. That is something that you've got to balance between in how small do I make the column and then I pay less, but then I pay every day in utilities, or do I make it bigger and I pay more but I use less utilities. There's a balance there that you'd have to look through a kind of a cost analysis and probably look at things out over multiple years. That's just kind of some engineering the questions that you'd have to answer and solve. But basically, that's what the difference would be. You can make it bigger, you would lower the energy. So does it make sense to do that? You can look at a column and you can just simply increase the number of stages. If it makes no difference in the amount of energy used, really, then you can make the assumption that that's probably not something that you'd want to do. You're paying for more column without getting any benefit. But if you start making it much smaller and the energy starts going up Now, obviously, you've got something that you may want to look at. Is this sound? Should I do this? Is the cost of energy really high? Is the cost of energy cheap, depending on what your energy source is? So those are the things that you'd have to balance. CHEMCAD can tell you what the energy is, but it comes down to money.